Hi, class. We're going to talk about the normal distribution today. And remember that your exam, the Unit 3 exam, is on chapters 5 and 6. And so this is uh, a short chapter. Chapter 5 just has two sections. And in 5.1, we just have here, again, they say, what is normal? And so I just want to talk a little bit about uh, this idea of normal, and they're referring to a probability distribution. So in statistics, we talked about probabilities and how to find them, and we said that there's a kind of a traditional approach or more theoretical involving formulas like the addition rule and multiplication rule and so on. And there are some problems with using those ideas, and the biggest problem is the size of the sample spaces. We based a lot of our formulas on taking how many we were looking for in the sample space divided by total number. So that total number can get very extremely large very quickly and well beyond what our technologies are capable of handling. So even with computers and calculators, we don't have the advanced technology that we would need to do a lot of these problems in the traditional way. So, statistics, we kind of use a different idea and we approximate probabilities using these probability distributions. And there are lots of different ones. And the most popular one is referred to as the normal distribution. So again, it is a continuous probability distribution, and we can use it to help us approximate probabilities and otherwise we wouldn't be able to do. So what we have to think about first is, okay, when we say normal, what's that shape? And they give an example here on page 176. And they say if you have a bunch of responses here kind of in the middle, and as you move in either direction away from the middle, so to the right or to the left, if your data values, the number of data values falling in each of these categories, they drop off very quickly as you go away from the middle. So this is kind of, we refer to as this is a normal like kind of distribution. So this is days before or after due date. Okay. So this is kind of a shape of a normal distribution. And we're going to, so running a little slow. So on page 177, they say, okay, here's this normal distribution. And you'll notice that we had that bars, like it was a discrete distribution. Remember a frequency table. Frequency table had categories or groupings, and then a listing of how many fell in each of those groupings. So you can think of, again, this bar chart, its histogram, is a picture of a frequency distribution. Each one of these bars is a group or category. And so we have some finite number of these bars. There's a lot of them, but there's some countable number. And then we could say it's discrete distribution. And then we take this curve and we kind of superimpose it over top of those bars. So the height of the curve is almost the height of the bars all throughout here, this distribution of data. And some are pretty close here. This one looks like it's right on. And the height of the curve right there is not too close to the height of the bar right there. So yeah, so it is overall pretty decent, right? So that's kind of what we're looking for. Now, are there other continuous curves, not normal distribution? Yes, there's lots of them. But this one seemed to fit pretty well. So then we got to say, okay, now we've got this curve, and how do we use it then to find the probabilities? Well, we want to know the height of the curve, if possible. The problem is the curve is a continuous distribution, which means there's an infinite number of possibilities. And it'd kind of be nice if we had a function where we could just plug a value in and get a number out. Anywhere along here, the input plugged like say 20 in, and we would get that number right there, and that'd be the approximate height of this bar, and it would relate to a probability. Now, if we look down here, you'll see this formula is not easy to work with, right? This is kind of a complicated formula, and we're trying to make statistics easier to work with. And so the reality of it is we're using this continuous curve because it's going to end up being easier for us to find probabilities in the long run. Now, we're not going to use this, okay, in a roundabout way we are, but so for right now, we're not going to plug numbers in here and then try to get an output. So let's continue on. And they're showing here that the middle of the distribution, the mean, right? We got that here, and we got a 75 here. So these both have the same mean, but they look different. So the center of the distribution is important, but we also need to know the variability. And you'll see this has a larger standard deviation. So the values are spread out more away from the middle. Here's a smaller standard deviation, same mean, but the values are tightly grouped. There's not as many of them deviating very far from the middle. So it says here the definition: normal distribution is symmetric about the middle. Okay, it's got this kind of bell shape to it. It's a single peak, corresponds to the mean. Its variation can be characterized by the standard deviation. Okay, all right. So let's go and look at this now. This is chest circumference of military men. So you'll notice that this kind of has that shape to it, right? This kind of goes up and back down, right? So not too bad. And then here's a population density listing of data. And we got the bar. You see, so this isn't very normally distributed, right? This isn't very normally distributed. So we have some higher bars here, then it goes down, then it goes back up, then it goes down in the middle, then it kind of goes up here. So population density is not, in this case, normally distributed. So what could we use it? Here's an approximation. No, it wouldn't work very well. So what we're trying to do, if we can find a population that is typically normally distributed, then we can use this normal probability density curve to help us find probabilities. All right. So this, again, definition says the normal distribution is concave up. And what that means is this thing is curving kind of upward this way, right? It's got this upward curve too. Let's see if I can draw on this thing while we're talking about it. So this, oops, this is kind of curving upward like this. Up, I guess I can't. All right. And but this part here is kind of curving down, right? It's curving downward. Wait, let me just. That's gonna work now, maybe. I don't know. Let's see if this works. If I can draw. And again, I'm trying to learn this stuff, so nope, it doesn't work on here. I could draw on here, that would work, but can't draw over this for some reason right now. Okay, we'll continue. So this part concaves down. Okay, it's kind of turned upside down. And this part again curves, kind of has this kind of upward slope to it. So that's all that's saying. Right. Now here's another distribution. It says the following normal distribution represents heart rates of students during a statistics final exam. So heart rate of students along here, well, it looks like 78. So is right in the middle. There's our mean. And the standard deviation is pretty small because we go out 1 each direction, get on 1 from 78 and go up 1. That's a big chunk of the data. 76 up to 80. That's almost all of the students' heart rates are in just a couple either way. So we would say that's a pretty small standard deviation, maybe about 1, size of 1. And then if you go from 81 to 75, if I go 3, wow, that's capturing pretty much all of the data, right? So, all right, so let's take a look at this. And again, we have a normal curve, and they're talking about the area under the curve now. So what are we, why are we doing that? Well, again, this is kind of different than the traditional probability approach. We're going to use area under this curve to approximate our probabilities. Okay? And it works very well. So it sounds a little strange at first, but it actually works very well. Now, all the area under the curve is 100%. So remember, our probabilities always range between 0% and 100%, or 0 and 1. And then, if this was nice and uniform, we could use geometry to find area. Just take length times width if it was a big rectangle. And but that doesn't seem to work here because this is standard geometric shape. So we're going to have another way to figure that out. And so since it wasn't that easy to come up with the, and again, these pages are turning a little bit slow, but we'll get there. Okay, is it normal? Again, scores on a very easy test. Probably not. Scores on it, that means everybody would probably score very high. And it would be way up. There'd be a few maybe lower ones, but it would be, the curve would be kind of curving upward. Shoe sizes of a random sample of adult women probably be normal. Most people would be, women would be around the same size, some a little bigger, some a little smaller. The number of apples in each of 100 full bushel baskets should be about the same and very little deviation. So if we counted the apples in 100 different full bushel baskets, you'd have some would be a little more, some would be a little less, but they would probably be fairly normally distributed. Okay. So we're just kind of getting a rough idea of what we mean by normal in terms of a normal distribution. But really, that's about it in section 5.1. Just a very, again, quick overview of what we're trying to do here. And we will slowly work through these pages. I don't know where the, in fact, let me check real quick. Okay, so the section 5.2 starts here, 185. So the idea now is we know what we're going to use to find probabilities. We're going to use these continuous distributions and then the area underneath the continuous distributions between inputs. And here's an example, normal distribution for replacement times for TV sets. And the mean is 8.2, standard deviation of 1.1. So 8.2 is in the middle. And if we go up one standard deviation, well, that's 8.2. And let me just move this over. But what they're showing here is that if you take and you have a line here, we're going to have to, if we put in the mean, okay, of 8.2, all right, so, and then the standard deviation, so I'm not going to keep jumping back to this, but 8.2 and then 1.1 years. So our mean is equal to 8.2. Standard deviation is equal to 1.1. Okay. And these symbols that I drew here, this is a Greek letter, so I'm referring to a population mean. This mu is the population mean, and this sigma is the population standard deviation symbol, right? So assuming we have like a population we know about, we put the 8.2 in the middle. And then if I take this 8.2 and I add one standard deviation, that's going to give me 9.3. Okay, so, and then I'm going to subtract the 1.1 from the mean. So I'm going to go above and below, and I'm going to put this in here. That's going to give me 7.1. All right. So this starts to help define our distribution. If we know it's normal, we know that a big part of that curve is going to be in there. Okay. And then again, if we go one more this way, and then we add 1.1 to this again, 10.4, we're going to subtract off 1.1 from this, and we're going to get 6.0. Well, by knowing the mean and the standard deviation, we know then that most of that distribution is going to be in here. So we've pretty much captured a large part of this, from 6 to 10.4. So those things that we were talking about over here are replacement time in years for TV sets, right? So now we can look at this distribution. We can say, well, this 8.2 really should be a little more to the middle, right? Let's see if I can. That's what I want. Let me just move this over a little bit. roughly here. Okay, so the middle, I get about right there. So what we're saying is that we know that TVs, almost all of them, last somewhere around 6 years to 10 years. So if you bought a TV and it had a mean of 8.2, you're thinking, well, it's supposed to last 8. I wonder if it'll last me like 15 years. And then you have this distribution. You'd say, well, it surely doesn't look like it, because even if I go up another 1.1, 11.5, and this curve, there's like nothing, hardly anything left out there. So if I bought this TV, right, with a mean of 8.2 years, and I think to myself, well, no, it pretty much isn't going to last. It'd be pretty rare, because it'd be like way out here somewhere. Or on the other end, you could say, I'm going to buy this TV. It's an average. How likely is it that it's only going to last me like 5 years? And again, you could go down this way, and I'm running out of room here, but 5 would be down here, way down here, and you'd say, pretty much, I'm going to get probably at least 6, 7 years out of this thing, even if it's below average. It's not going to be like I'm going to buy it and it's going to last 2 years or something like that. So it can help us make decisions about things if we know the mean and the standard deviation, right? So let's go ahead and take that off of there for now. And I guess I could, all right. Okay, so let's keep moving now. And so it seemed like, yeah, we got that idea now. We need kind of a standard of how much. We set a big chunks in the middle and so on. And when people started using statistics, they wanted something simple. And here they talk about this rule. This was like the rule that everybody knew. If you were using statistics and you were talking about um, probability, then you had to kind of really learn this thing first. And we didn't be real picky. We were just as simple as possible. And it says a simple rule called the 68, 95, 99 gives you precise guidelines. Well, it doesn't give you precise guidelines that lie within. It gives you the values of those 1, 2, and exactly 1, 2, and 3. And they're pretty accurate though, for the most part. So this was a good way, and it was called the empirical rule. So let me just kind of write this. I'm going to go back here to writing and talk about this. Now, so let's see if I can get this. All right, there's our normal distribution, straight as I can get it. So the empirical rule, this is the standard normal distribution, right? Standard normal. We're going to put 0 in the middle. This again is the empirical rule. Okay, empirical rule. And if we have 0 in the middle, we have I'll write over here, standard normal distribution. Mean is equal to 0, standard deviation equal to 1. All right, so the whole thing is 100%. And That's good. Okay. So, but we need to break this thing up. So let's go here. We're going to come down to, again, one standard deviation above, one standard deviation below. Now, for any distribution, any application that you would use, okay, if you have your standard values, oops, oops, um, -1. So negative meaning to the left or below the mean, below the middle. One standard deviation above, one standard deviation below. And so the empirical rule tells us that the amount of area, okay, is pretty much 68%, okay, of all the area under this curve. 68% of it is going to lie between -1 and 1, or within one standard deviation. Okay. And then, so that's good to know. And 2 to -2. Let's make this thing down. Okay. So from 2 to -2, this is an important rule. 95%. Wow, that's almost all of it. Okay. And that's how I knew earlier when we were talking about the TVs, how long they lasted. So I knew that roughly 95% of those TVs were going to last within 2 standard deviations, okay, because it was basically normally distributed. And so when I look at any example, not just TVs, but anything that's normally distributed, I can figure out pretty quickly some numbers, right? I can figure out plus or minus 1 standard deviation, like in the last example with the TVs, plus or minus 2, and then I can make a lot of decisions based on the length of time that TVs are going to last. 8.2 years was in the middle, remember, with 1.1 standard deviation, right? Those numbers aren't exactly the same here. Those are non-standard normal. We're talking about the standard normal. This is what is the baseline or the guideline that everybody uses. And then if you go up to 3, and it theoretically doesn't touch there, it's still open. All right, so against that, it's still open, but not much. -3. So from -3 to 3 is 99%. 99 and a little bit more. We just say 99. The book has 99.7, so even more of it. So that's basically the empirical rule, and that's what we would use again in trying to figure out some just basic probabilities for items that are normally distributed. So again, it's very popular. It's still being used, but the only thing about the standard normal, this empirical rule, is that it doesn't let you get very precise. Because what if it was like 1.5 standard deviations or 2.37 standard deviations? Then what's the probability? Well, you can approximate. You can break this thing up and get into approximations and so on, but there's an easier way to do that. Okay, so we're gonna. All right, so let me get up to this thing. Jump back. Let's go to 185. Let's see. And There, okay, so 186. Okay, let's just talk about these examples. This is applying that rule, that 1 and 2 and 3 standard deviation rule here. Normal distribution of test scores with a mean of 75 and a standard deviation of 7. Okay, so they give you this information here, right? So 75 is in the middle, right? So that's the mean. So we put that in the middle. And then if we have a standard deviation of 7, they're showing you here, if you take this middle, the 75, and add 7 to it, you get 82. Okay. And if you add another 7 to that, you get up to 89. And add another 7 to that, you're pretty much nothing else out, but it's 96. So for the right side of this, the plus standard deviation, you see the pluses here. Well, we got our numbers already taken care of. I don't have to do any more. Now, if we go on the left side, those are the subtractions. 75 minus 7 is 68. And then minus 7 again is 61. And then minus 7 again. So what we're doing is we're going 3 to the right, 3 additions to the right, 3 subtractions, 7 to the left, right? So then we can talk about the exam scores. We know that 68% of the scores were between 68 and 82. So we know where a lot of the students scored at. Now, almost all of the students scored between 61 and 89. So we can tell how likely it is 95% chance that a student, if they took that exam, was going to fall in here. Okay, 61, 89. And then these smaller percentages, right, once you get out between 2 and 3, there's not much out there left. 99%, right, between 54 and 96. Then you might have some outliers beyond that, but we're able to get a pretty good idea of what the data set looks like. And that's really what, remember, when we collect data, one of the first things we do is we organize it, and then we try to interpret what we got. And the normal distribution can help us really interpret, just like we had when we had histograms and things like that. Okay, but it also has given us a way to compute probabilities, right? All right, we're going to continue forward, and we're going to look at those standard scores again. Let's say that I have this is a formula, and remember this formula was on the last test, I think. This was the z-score formula. Z, if you remember, x minus the mean over the standard deviation. Okay. So if I'm working with some data, like the length of TVs, how long are they going to last, then I want to use the empirical rule, because I know that 1 and 2 and 3 standard deviations. Of course, I can add that stuff up myself and all that. But what I could do is standardize it so that everybody can understand what the numbers represent without having to go through figuring it out themselves. So when we created the little normal distribution with 8.2, and then we added 1.1 to it, and we added 1.1 again, and so on. And on the test scores, we did the same thing, added to the right, added to the left. Well, we can just standardize it and then figure it out that way. So it's just another option of how to interpret this normal distribution, but the z-score is very important. So here we have an example. It says the IQ test have a mean of 100, standard deviation is 16. And we want to look at scores of 85, 100, and 125. Okay, 85, 100, and 125. So let's go up here, and here's our z-score formula. Okay, z is equal to, I'm going to do sample, oops. All right. So I'm going to take x, the score, minus the mean, divided by the standard deviation. All right, so now the score, the first score we're going to check is 85. So we're saying that the mean of the population is 100 for SAT scores, or whatever the scores are for, and 16. Okay. So we just simply take these numbers and plug them in here. So we're standardizing that 85. So we have 85 minus 100 divided by 16. And again, if you have your calculator, you get z equal to negative. So the negative means it's below the mean, which 85 is less than 100. 0.9375. Okay. So that's pretty much it for the z-score. It's pretty straightforward. And I'm not going to do any more of those. That's good. In fact, let's just clear this thing out. All right. Now, this is the IQ score. See, they were 85. 85 was down here. There was about 1 standard deviation to the left. So we see on the curve where it is. And so if we want to know how much area there was in here, right, then we'd have to kind of figure that out and look at this and say, well, you know, this is like 34%. This is 50%, because this is half. Remember, this is right in the middle. This is like 50% of all the area. And then this distance from here to here is half of 68, or 34%. So like 88% of the area is over here. Roughly about 12% scores over there. Okay. So let's take a look at percentiles. And remember, we did percentiles on the last test. So percentiles, the percentage of values at or below some given value. So if we were looking at this and we said, okay, there's 88% this way, 12% this way, then this number is also roughly about at the 12th percentile. How much area is at or below what we just said is 12%. So we could also say the net score is at the 12th percentile. So this is a nice, easy way to calculate percentile. And another way to do that too is we could just look at this table. Here's a z-score table. So we were kind of guessing about, well, here's a table we could have went and looked at too right away. So this says standard score in percentiles for a normal distribution, cumulative values from the left. So it's coming from the left, and we were at roughly about -1. This table is abbreviated. We were around -1.1 here. So this is a little off from what we got. This is saying 13%. Because we need to get it was -0.9. So we need a better table, and I'm gonna get one right here if I can just pull this up. I'm Googling z-table, okay, and I'm gonna pull one up and show you. So this is a better table. This one shows -1. It was -9.3. It was, what did we come up exactly with? Negative 0.9375. Negative 0.937. So we are about right there. So this is a pretty accurate way. We were kind of guessing. The table lets us go out, like it's showing 1, 2, 3, 4, 5 decimal places. So we have much more accuracy. So this is about 16.6%. Okay. And again, we would kind of roughly guess 12. We were, again, that was a pretty close guess for a quick estimate. So that's where you would get that from. And z-tables, there's a better z-table in your book in the appendix. This is for the negative side, and this is for the positive side. And if we looked at 0.973, about 82, we said 88%, so that was closer to the 1.1, so that was pretty darn close to 88% there. A little bit above the 1 on both sides, right? We could check this. Okay, let's go ahead and continue. Now, the z-score, let me just pull that back in over here again. Before the calculators, we had to use the table. And you can use the table on the test, or you can use a calculator. But this is how people did statistics. If they were trying to find probabilities or area under the curve, and not just for the normal distribution, your books had lots of tables. They have lots of tables for all the different continuous distributions. And that's what you would do, is just go to the table. And when I taught statistics years ago, that's all we ever did was went to these tables. And basically that formula, that really interesting looking formula a while back, I, I showed you, since we can't use that probability formula, we uh, they went and just calculated the normal distribution goes roughly from -3 to 3, and maybe a little more. You notice this only goes up to 4. The table in your book doesn't quite go that high. Uh, most tables go to like maybe 3.5, because you notice, look how small these numbers are once they get, look, like almost 0. These are almost all zeros. So that's why these aren't even usually in the book. They aren't in the tables. They go up to like 3.5. And so when you want to define a probability, you just come to the table, and then that would be your probability. No formulas, really nothing. You just have to have it standardized. And then they thought, well, with the calculators, we don't even need to standardize it. We can just avoid all of this using the Z table, the Z score formula, then go to the Z table and everything. So that's what we're going to do. A couple problems like that, and then that'll be about it. All right, so let's go ahead and move forward. All right, so using technology to come up with standard scores and percentiles. Now here's the 8384, and I'll show you how to do that in just a minute. So we're gonna, oops, let me go back. Okay, so okay, I'm actually going to just get out of the text here, because I'm going to go back to do these. It'll be easier to just do these by hand. And I'll pull in the calculator. Let me get that. The TI-84. And again, some of you have different calculators. And this is starting up. All right, let me bring this over and see if I can write here beside it while it's open. And let's see what we got. Okay, good. Now let's go back to that TV example. We had a mean of 8.2 and a standard deviation of 1.1. And we wanted to find some probabilities. Okay, so oops, let's see. Now in your calculator, you're going to hit second function distribution. Okay, the vars key, but you'll notice right above the vars key it says distribution. Right, so that stands for the probability distributions. And then we look over here, distributions. Okay, good. So that's what we want. And there's lots of them. You see how all the different distributions are they have just in this calculator. And it goes down for more of them. But number 2, normal CDF stands for normal distribution cumulative density function. Okay. So what I want to do is we're gonna come into this just for a second. I'm gonna come back over here, but we're just gonna have to, we'll pull that up. I'm gonna get on to number 2, all right, and hit enter. And your calculators may be a little different, but it's going to end up being the same. So just hold off till I do this count. This is the brand new one. So if you have a newer TI-84, this is what it looks like. And I'll tell you what this all means here in a second. Okay. So I'm going to draw a normal curve. And I have this information. So let's say that I want to find how likely those TVs are going to last from 7 up to 9. Okay. 9. Okay. So in essence, what I'm asking is, how much area is there in here? All right. It's all in here. And well, we know the middle is 8.2, right? It's in here. 8.2, and the standard deviation is given. So finding the probability of coming up with a value or a TV lasting between 7 and 9 years. Right? Well, I would have to go to the Z table and convert these over, and I'd have to look up at the table that I showed you and all that, but this is actually much easier. So my lower number, or the one to the left, is going to be 7. Okay. The upper number here is 9. Okay. The mean is 8.2. Standard deviation, 1.1. And then paste. So the newer calculator runs you through one more screen than the older ones do. So the rest of you with the 83, 84s, when I hit enter here, it's going to take you to what you really should have put in. So your calculator comes up looking like this, and then you put lower here, the upper, just like we did on the other screen, except you're writing yours out this way. Here's the mean and the standard deviation, and then we hit enter. Both people, regardless of the calculator, you hit enter and you're going to get this 0.6288. Okay, so this area from here to here is 0.6288. Okay, so that's our answer. 62, roughly 62, 63% of all the TVs are going to last between 7 and 9 years. Okay, so see, it allowed us to get more we didn't have to go 1 standard deviation, 2 standard deviation, 3, and just look at those and guess. So this is the actual probability, right, between there and there. That's it. It uses the statistical function to calculate, and this is not an approximation. Again, this should be assuming that those TVs are normally distributed times, and that's your answer. Okay, great. So let's go back and do another one. All right, so we had the SAT scores. We had a mean 100. Standard deviation was 16. And we were looking at that problem, and I was saying, oh man, where was that score of 85 at? Mean of 100. 85. What was the percentile? We were trying to find a percentile. Here's 85. And we wanted to know how much area there was to the left of 85. Okay. Oops. And so all this area is what we're trying to find here. All right, you get it. Percentile, how many scores or what percent is at or below or at or to the left. So if we can just find this with our calculator, we make that a very easy problem. So let's get the calculator in there. I'm going to clear this. Second function, distribution. All right. Number 2, enter. All right. Now the lower, now you have to kind of watch what I put in here. Negative, this e right here, which is second function, comma key. So we get negative little e 99 up to 85. Okay, why did I do that? Well, there's no number over here. I don't know what to use, so I use, this is the standard, negative E99 in these calculators, right? Which stands for negative infinity. Okay. So the mean, let's go through and 100, 100, standard deviation of 16. And again, that's the people with the newer calculator. Enter. All right, if you have the older calculators, doesn't have to really be that old, just ones that don't have the updates on it. But again, so you put in first negative E99, 85, which is the upper bound, mean and standard deviation, right? So, and we get enter, and we got 0.174. So 0.174, and this goes out. This is where the E negative E99 is. So it's how much area is there from negative E99 to 85? Well, about 17 and a half. And remember when we did the table, and we were kind of roughly estimating a little bit, it was like 16 point something. So it was a tiny bit off, but really pretty darn close. But this is a more accurate, this is an easier method. I know the calculator looks a little tricky at first, but really it's not quite so bad as you think. Once you do a couple of these, you'll catch on. And we're going to do one more, and we're going to do area to the right. So I'm going to clear this out and clear that canvas. And we're going to do area to the right. So the problem in the book that we were working on, and I got to look real quick, it was 1.56. So the IQ, the score was 125. All right, so let's do that one. Let's do the same thing. We had a exam score. The exams had a mean of 100 and standard deviation was 16. I'm going to change the score to 125. Okay. And again, what I'm doing here is assuming that it's normally distributed. I'm going to, again, the middle is 100 and 125. And we're going to do the area to the right. I want to know maybe what that top percent is. scores above 125. How many people were above 125? And it's pretty easy to find. I can just use my normal. So if you guys have the older calculators, or both of you actually, it gets to normal CDF. We're going to do 125, E99, 116. All right, so again, here's 125 up to, so I don't have any numbers up there to look at. E99 is positive infinity. I'm up here to the right. And then I plug it in and I hit calculate, and that's it, right? So it makes it very, very easy. So let's go ahead and plug it into the calculator, and let's clear this out and do second function, distribution, number 2, enter, and we're doing 125 to E99. And that's 100. And that's 16 again. And I'm going to go to paste. So there's everybody's got, should have that in their calculators. Hit enter. And 0.059. All right, so 0.059. So from here to here and up, 0.059. So there's not much, almost 6% of all the scores are going to be above 125 on IQ. So not very many, not a lot, right? Okay, great. All right, and that's going to close out that chapter for today.